My name's Professor Richard Holich. I'm a Professor of Chemical Engineering at Loughborough University in the UK. I'm also the Chief Technical Officer for Micropore Technologies, and I'm talking about membrane emulsification, specifically for encapsulated products. And Micropore was formed as a spin-out company from Loughborough University, and the university is about 100 miles north of London in the UK, and the company now trades from somewhere just slightly south of the city of Derby. So we've moved off campus 3 or 4 years ago, but we formed the company back in 2003 in the building on the right hand side there. The outline of the talk is I need to say a few words about membrane pore size, microfiltration pore size, and its bearing on the process of emulsification. And then when looking at membrane emulsification, I would like to cover dealing with laboratory tests at the small scale, then scaling that up to something that is a process scale, and a little bit of understanding or modelling work of the process to help us with that scaling up and sizing aspects. Then for encapsulation, I'm going to concentrate on coacervates, which are suitable for food uses, for example. Then we have a polylactic glycolic acid, PLGA, which is a pharmaceutical biocompatible polymer, the application there being a controlled release. Then another application, silica microcapsules, porous silica is used now in a wide variety of different industries. And the last example is a surfactant-free stabilisation of an emulsion, which is done by a process called Pickering Emulsions, as we'll see. Okay, well, here is a conventional microfilter, and the problem here is the surface. You can see here a pore opening, which is the dark bit in the middle here, which is probably round about up to 25 microns. There's a scale bar here at the top. So that's a 25 micron pore opening, but there's plenty of other sizes of pore openings on the surface of this membrane. This is a sintered conventional microfilter, and in membrane microfiltration this wouldn't be a terribly big issue. It just means material gets stuck inside the filter. But in membrane emulsification, this is a critically dependent on the surface of the filter process. So this irregular surface becomes a bit of a problem to us in membrane emulsification. Here you can see an example of another conventional microfilter, another scale bar here, 100 microns in size, and here you can see that there's a very irregularly shaped pore, easily 50-60 microns in pore length, and yet if you look at the ASTM, the old ASTM 316, then it gives an apparent pore size of about 3.5 microns. So according to the standard technique for sizing microfilters a few years ago, all the pores in this membrane were only 3.5 microns in size, and in fact the manufacturer rates this as being a 3 micron size filter. If you were doing microfiltration, then you could easily capture particles of this size inside the matrix of the filter. So it's not really a surface filtration, although sadly we talk about these things as being a 3 micron pore size filter, and that kind of implies sieve. Reality is the microfilter isn't a sieve. What it really has is a depth. It's like a sponge, so it's capturing those sorts of particles inside the sponge network. And if we're going to inject an oil phase through this microfilter, as indeed we do for membrane emulsification, then this becomes critically important, because it's the surface of the microfilter that's most important to us for membrane emulsification. So back in 2003 then, we set up a company that was dealing with microfilters where literally we were talking about sieves. So if this was a 5 micron filter, that is exactly what that pore size there would be, and it is literally a hole of 5 microns diameter amongst lots of other holes of 5 microns diameter. And likewise here, for filtration we normally use slots, and this one here could be a slot of say 4 microns diameter, something like 400 microns length, and again it's all uniform, all the same size, and straight through. There's no depth, there's no sponge-like network behind the opening, behind the pore. For membrane emulsification we tend to use this style, the hole style, but if we have suspended particles that we're trying to also put into the emulsification, we can use the slots. The slots are still of use, even in membrane emulsification. The actual process itself is probably best illustrated here. If you look very carefully at the centre of the most visible circles, you'll see a very small pinprick hole, which is where the oil is emerging from. This is the process of membrane emulsification. We have an oil phase here that's being injected into an aqueous phase. It's being pushed through those little pinprick holes in the middle of the exterior hull, and as the membrane is all very uniform in size, you can clearly see that it's producing some very uniform droplets of oil dispersed in water. And if those oils are a monomer, then it's possible to polymerize those droplets to form a polymer, to form a solid surface, to form a solid particle. And we can do encapsulation based on this technology as well, by providing those uniform particles with some form of structure that's capturing the internal phase. This is without any shear applied onto the surface, so the drops just grow as big as they can until eventually buoyancy pulls them off. So what we saw a few moments ago was really the process taking place just here, with the oil phase coming in and being injected through the membrane. In the previous slide we didn't actually have any shear, so the drops were just getting bigger and bigger, but clearly it's possible to put a stirrer on the surface here to help dislodge those drops, and that's what's illustrated here. So in other words, this is the membrane down here, here is the stirrer, simply connected to a fairly straightforward motor at the top, and we can put this into a laboratory device where it's just driven typically by 3 volts, 6 volts, and the current draw is much less than 1 amp. So what you're looking at here is about 100 millilitres of liquid, and you can clearly see drops are being dispersed into this, what we call the dispersion cell. The electric motor's up here, it's just a simple DC motor, hence the control with the power supply just there. And the oil phase is being pumped in through here and underneath the membrane for that dispersion to take place. So that's the simple laboratory device, which really is appropriate for testing out membrane emulsification. So that's very much what we say is a formulation testing device. And just to give you some example, all these scale bars here are the same. They represent, in fact, 100 microns from one end to the other of that scale bar. The only difference between the slide on the left all the way through to the slide on the right is the shear stress in the units here of dynes per centimetre squared. So the membrane was the same, it was done inside the same dispersion cell, it's the same chemical formulation. All we've done is increase the shear stress from 13 to 146, and in doing so we change from droplets which are clearly bigger than 100 microns through to droplets which are about 30, maybe 40 microns in diameter. And you'll also notice the uniformity gets better as well. There's a sort of optimum value here as well. So instead of looking at it visually, if we looked at it down a laser diffraction system, a Malvern as it happens, we can see here the D50 of 87 microns with a span of 0.36. So they're not absolutely monocised spheres, but they are very uniform spheres. Well, when it comes to trying to understand how the process operates, there are quite a few forces in play here, but the two that are undoubtedly the most important are the capillary force, which holds the drop onto the surface, and also the drag force, which is what eventually drags the drop off that surface. So there's a buoyancy force, there's all sorts of other additional forces that you could bring into a comprehensive force balance model, but these two are the most important. And if you inject the drops significantly quicker than, if you inject the drops reasonably quickly, then you'll move from what's called this dripping regime, drop being produced, drop being produced, drop being produced, into a jetting regime, which is where the jet comes out of this membrane pore in a much faster way. So productivity obviously increases when you're injetting, but the drop size distribution normally suffers, normally becomes wider. There's also this effect called push-off, which is when there's just so many drops present here, they're almost, well, they are touching each other, and they push each other off. Okay, so that's another force, really, which is deforming the natural spherical shape, and because of that it's energetically doesn't like to be deformed away from its spherical shape. It creates another force which can actually push the drops off. So the basic model, capillary force and just the drag force, this predicts the drop size diameter. It says it's a function of the shear stress. Well, we've seen that with the dispersion cell results. The radius of the pore, the smaller the pore size in the membrane, the smaller the drops will be. And the last parameter of great importance is the interfacial tension. The bigger the interfacial tension, the greater the interfacial tension, the larger the drop size. This model doesn't have injection rate in it. This is literally the predicted drop size, smallest drop size, for the lowest injection rate, the lowest productivity, if you like. It's not a bad model. Here are three different microfiltration membranes, these two pretty big, and the data actually fits it reasonably well. Not so well at the very bottom agitation speeds, which correlate with shear stress, and that's because this was in fact an 80 micron pore spaced membrane, so any drop bigger than 80 microns, or even at 80 microns, is going to be deformed. So this was the sort of push-off effect that I was talking about, is relevant when your drop sizes are equal or bigger than the spacing between the pores. But whilst the drop sizes are significantly smaller than the pore size, then there's no problem. So the model works reasonably well. Okay, so scaling it up from a laboratory system into a more commercial system, if we were looking to provide cross-flow on the membrane surface, that can give us a consistent shear, and of course the drop size is shear dependent. So here are in fact 4 tubes where we have a cross-flow consistently going, and it goes round and round from the progressing cavity pump that's down here, through the module up here, and back into the feed tank, which is just here. And this is a cross-flow system with continual recycle, and it's possible to generate an emulsion up to something in the order of 100 kilograms per hour through these 4 tubes running in parallel. So it's a reasonably high production rate compared to other techniques for monosized drop production. So that's cross-flow for generating the shear. Consistent shear on the membrane surface. Here's a very different way of generating shear at the membrane surface. It's using oscillation, and if you look very carefully you can just about see, just down there, where the drops were streaming off the surface. These are drops that are sinking in the continuous phase. This one in fact is a water phase being injected into an oil phase, and you can see the drops just here that were coming off the membrane surface. So clearly the shear rate isn't constant in that previous technique with the oscillation. The shear rate's varying, True, but it's varying consistently over the whole surface of the membrane. So we have a peak shear rate, which is about 6,500 seconds to -1 here. Shear rate and shear stress are proportional, so we do tend to sort of swap around between them. And it's shear stress or shear rate that's important for determining the particle size, the drop size. So here we have a shear rate which goes up to a maximum of 6,500 seconds to -1, and so long as there's a what we call peak shear event that's more frequent than the drops emerging from the membrane, then each drop will be subject to a peak shear event, and that will break the drops off at the same position, at the same size. So it's the highest shear rate that's important. And just to give you an idea of how the drops from that oscillating system look like, they were aqueous phase, which is PVA dissolved in water being injected into kerosene, and here is an illustration of the drops under a microscope, and you can see they're pretty uniform, not completely uniform, but pretty uniform, with a productivity in the tens of kilos per hour from a single small tube. Okay, well, instead of pulsing the membrane, it's possible to keep the membrane stationary and pulse the continuous phase over the surface of the membrane. And so this is just going backwards and forwards. So there is a fairly gentle left to right flow, but on top of that there's also this oscillation backwards and forwards. It's a bit like AC and DC electrical current. There's a sort of AC movement and a slight DC current, which in our analogous terms here is taking the liquid from left to right. So that means we can generate quite high shear whilst having quite low flow rates through the system, and that quite high shear means we can create some small droplets, and we're still using this same sort of membrane, the Micropore uniform pore size membrane. And the illustration here is that we need a dispersed phase system that's pumping in, and the continuous phase, which is what's being oscillated at the same time. So this is our means of oscillation. So this is oscillating as well as moving gently from left to right. Why do we need to do that? Well, in a single pass, in as much of moving from left to right, we're not having to recycle the continuous phase as we would do in crossflow. So in a single pass, in terms of the continuous phase, it only goes from left to right once, albeit moving backwards and forwards rapidly in the process of doing so. We can go up to something like 40% by phase volume emulsion. We can go even more if the surfactant can stabilise it. Okay. And that means we haven't had to put the resulting emulsion through a pump. If this was crossflow and we were recirculating round and round, sure, we could get up to 40% phase volume, but in doing that we would have had to have recirculated the emulsion through the pump many times over, and in doing that the pump itself probably would have destroyed the drops that we've carefully produced with our emulsification system. So this means that we can now look at different types of stabilizers, the sorts of stabilizers that are less common, less effective, if you like, in stabilizing the droplets, and for food and flavouring purposes they tend to be the more natural products, the ones that are easier to market. So stabilizers which are less effective can be used in this system, because all they're having to do is stabilize the system in a very gentle way. They're not having to stabilize drops as they go through pumps and valves and fittings and things like that. And what we have here is an example of the pulsed system. This one is fairly low dispersed phase volume, 1 to 2%, but these are actually quite large drops. These are about 1 millimetre size coacervates, so they are in fact a a dyed mint oil, dyed in blue mint oil coacervate, 1 millimetre roughly in size. If that went through a pump, the pump would undoubtedly destroy them. Here are some smaller coacervates. They're around about 100 microns in size, and they're reasonably uniform. The illustration really is that we can produce, by membrane emulsification, controlled coacervate size from sub 100 microns all the way above 1 millimetre. And those coacervates are encapsulating some food, flavouring, fragrance, that type of thing. This is an interesting one, water, oil, water emulsions. And this particular one is PLGA, polylactic glycolic acid, which is a biocompatible polymer. And it's really appropriate for the subcutaneous, using controlled release of active ingredients under the skin, subcutaneously under the skin. So that's an interesting trade-off, because you need a reasonable sized particle to have a significant enough payload for the controlled release, but at the same time it's got to go through a needle. So if you want a needle that isn't going to cause too much pain when these particles are being injected, then clearly you want small particles. So it's this balance between small particles which have ease of injection but big enough to have a significant enough payload, and around about 60 microns diameter is the sort of optimum size between those two. So what have we got here? We've got this usual micropore style membrane, straight through membrane. We have a primary emulsion which is illustrated in this sort of purpley colour inside the yellow. So the yellow here represents an oil phase. That purpley colour is in fact an aqueous phase inside the oil phase. So this is a primary emulsion, and we're using the Micropore membrane emulsification system to create the secondary emulsion. So this is literally a water in oil in water again, the surrounding phase here, emulsion, a water, oil, water, or WOW emulsion. And the clever bit here is the low pressure drop, the ease of generating that secondary emulsion. Because it's such a straightforward system, we don't risk poor encapsulation efficiency, because the worry is that the water internal phase, one of these little drops, goes into this external phase here, and that would cause us low encapsulation efficiency. We'd have leakage of the primary emulsion into the secondary water phase. Again, high shear systems, they'll give you that. They'll lead to poor encapsulation efficiencies, but this is such a gentle technique for producing emulsions, easy to control, that we can create very high encapsulation efficiencies at 100%, approaching 100%. And here are some examples. This is the internal water phase just here. You can see these droplets of water. This is the external oil phase just here, and here is the external water phase that oil droplet is sitting in. So it is the full water, oil, water emulsion. And by doing that, we end up with this sort of structure here, which is looking under a SEM, scanning electron microscope, and we can see that there's clearly routes here for controlled release of the encapsulated material inside. The encapsulated material inside would be inside these water drops here, typically a peptide, polypeptide or protein type of treatment, which would have a controlled release over a certain time. If we didn't have this emulsion looking like this, this is just the ordinary oil in water type of emulsion look of the particles. Again, still possible for controlled release, but this would give us a much slower release. So clearly we can sort of tailor the release profile. When it comes to looking at the release profile, it's a classic sort of engineering approach in terms of a diffusional equation, and we have to take into account the swelling of the particles, but swelling of the particles, diffusion, and in fact degradation of the particles, because PLGA does degrade. Acid degrades, auto acid production degrades. Well, here's another method of drug delivery, amongst other things, porous silica particles, mesoporous silica. Here we can see some silica particles produced via membrane emulsification again, pretty uniform in size, and if we just look at the one particle there, this is what it looks like, nice smooth spherical particle. And if we just focus in now at that little surface there, this is what this much higher magnification looks like, and you can now begin to see the surface structure on these smooth particles, and you can begin to see openings, and this is appropriate for our controlled release. Inside that silica particle we have active ingredients, and the active ingredients can be attached to the silica particle and released from the silica particle when in situ. So this is drug delivery using silica. Another option is surfactant-free. Lots of particles at the surface of our oil drop. So having created an oil drop, if that oil drop is inside a suspension of particles, those particles can partition themselves between the oil drop and the surrounding aqueous phase if they've got the right surface charges. And that's called a Pickering emulsion. It was actually something that was published originally by Ramsden, but has become known really as Pickering emulsions, which is these. There's no surfactant there other than solid particles, and it's possible to play around with the buoyancy of these particles. You can have ones that don't move up and down. You can have ones that sink, or you can have ones that even float. And we've done some interesting work there, creating some floating particles for photocatalytic effects. This is where we have titanium dioxide, which acting as the stabilizing particles. It's surfactant free, but the titanium dioxide particles are partitioned around the oil droplet, and they've caused the oil droplet to remain stable. The oil droplet's floated. It's a vegetable oil, it's not a mineral oil. And then the TiO2 has in fact photocatalytic properties, so it's at the surface where you want it, because the sunlight is obviously above the liquid level, so the sunlight can come in and we can use the floating particles to interact with that sunlight for those floating photocatalytic properties. So titanium dioxide would normally sink. I mean, here's some residual TiO2 particles down here, but this is encapsulation by solid particles. So membrane emulsification. For encapsulated products in particular, what's its advantages? Well, it's a very low energy process using the style of membranes that I've just discussed. One of the reasons behind that is it's a low pressure process. We are really using sieves rather than depth microfilters. Formulation is still important. It still requires some good laboratory testing and understanding of the chemistry, but that can be done at the small scale, and then we can scale up through to tens of kilos per hour, hundreds of kilos per hour, or even tons per hour production using the same membrane emulsification technique, just a different way of applying the shear onto the surface of the membrane to create those drops. And the variety of shear we've been talking about, well, a stirred system for laboratory testing, oscillation and pulsation primarily for production, although crossflow's okay so long as you don't mind a bit of breakage of the particles of the droplets in the pump. Why does membrane emulsification win over certain things? Well, multiple emulsions, much easier to make multiple emulsions using membrane emulsification, and it lends itself also to continuous production. This is going back to the pulse system, where we had 40% phase volume being produced in a single pass. That can then be passed into a polymerization stage or a reaction stage to create the particles. And finally then, it's good for small and large drop production. How small? Well, down to about 10 microns. Thank you.